The relaxation properties of MR are what give MR its unique soft tissue contrast. So every tissue has a unique, or every molecule has a unique set of spin lattice, T1, and spin-spin, T2 relaxation. So going back to our original experiment where we put a bottle of water in a coil, we've excited the system by giving it energy for a small amount of time at the Larmor frequency, and then we wait. We get a dampened sinusoid signal back. Well, as soon as that energy is transmitted and received, the water molecules will interact with themselves and lose energy to their neighbors. That is essentially a layman's view of what spin-spin relaxation is, because each spin will lose energy to its neighbor because it's moving in space. That is going to give you the dampening, part of the dampening effect of your sinusoid, the free induction decay. Decay meaning that it's going to decay, and it's essentially inducing the current, because the whole effect is that you have a magnetic field that's moving perpendicular to another magnetic field for a transient amount of time. By Faraday's law, that's going to induce a current. If you have two moving magnetic fields against a coil, against a current, it will induce a current. And that current is what you're essentially listening to, but it's very minimal amperage, so you don't have much power. So you need to amplify that. Spins will lose energy to themselves, and that's spin-spin relaxation, and that's T2, 1 over, and then the amount of time that it takes the spins to go 1 over E of their energy is T2. Spins will also lose energy to essentially the lattice back to the molecule themselves, and that's T1 relaxation. And so not losing energy to a neighboring spin, but losing energy by definition back to the amount of time it takes for the magnetization of that one proton to go back 1 over E to its resting state is T1. And then T2 star is T2 plus magnetic field inhomogeneities that occur both by the system itself. So the system can't be perfect. So the B0, if I was imaging that bottle of water, the B0 here and the B0 here are not exactly the same. So therefore, since they resonate at different frequencies, those different frequencies will induce different relaxation rates. In addition, when you have gas or anything that causes susceptibility change, what's referred to as susceptibility change, meaning gas, which cannot have magnetization because it's gas, essentially, so it has no magnetization, and therefore, anytime you have a very sharp gradient in magnetization, you will cause a loss of coherence of magnetization. So gas, bony interfaces, all cause, and metal. So if you have tiny amounts of metal, iron in your body, not only macro iron, but a liver, let's say a liver that had a lot of iron, all of those would cause subtle changes in the resonance frequency or the B0 field, the static field, and therefore would cause more rapid loss of T2 relaxation, and that's T2 star. So T2 star is essentially always shorter than T2 because it's T2 by nature plus all of these other things that cause more variability in your spin-spin interactions. So you have all of these relaxation properties, and then therefore, going back to the experiment that we talked about, you can vary in the pulse sequences, you can vary either the repetition rate or the other factors to weight an image to to differences in the relaxation rate. For instance, you can make the free water will have a different T2 than fat, will have a different T2 than bone marrow, will have a different T2 than myelin, and therefore you can heavily weight an image, meaning that you can make the contrast most specific to that property. and therefore on a T2 weighted image, things that would have a long T2 would be bright because they would preserve signal, and things that have a short T2 would be dark because they've lost their signal. And therefore you're exploiting that contrast by weighting it heavily towards that contrast mechanism. Similarly, you can weight, by varying the repetition rate, the T1, and therefore weight things that have short versus long T1s and make your image contrast based on that. And as you get more and more versed in MR parlance, you get comfortable with what normally is a T1 weighted image versus a T2 weighted image, and the things that are normally short, that have short T1s, like blood, like fat, and things like that.